Welcome! In this session, we'll explore LeetCode problem number 247, Strobogrammatic number 2. This problem challenges us to generate all strobogrammatic numbers of a given length. We'll review the problem, break it down, and discuss efficient approaches to solve it. Let's dive in. A strobogrammatic number is one that appears the same when rotated 180 degrees, meaning it reads identically upside down. For example, the numbers 69 foot, 88, and 818 are strobogrammatic because their appearance doesn't change after being flipped. The goal of this problem is to find all strobogrammatic numbers of a given length n. For instance, if n equals 2, the valid outputs are 11, 69, 88, and 96. Each of these numbers satisfies the condition of being strobogrammatic because they maintain their structure when rotated. Now, if n equals 1, the valid strobogrammatic numbers are 0, 1, and 8. These single-digit numbers remain visually unchanged when flipped upside down. For another example, when n equals 3, the objective expands to finding all strobogrammatic numbers of length 3. This involves considering combinations that remain symmetric when rotated. The solution must account for all such possibilities. For n equal to 3, the valid strobogrammatic numbers include 101, 111, 181, 609, 619, 689, 808, 818, 888, 906, 916, and 986. Each of these numbers, when rotated 180 degrees, either remains the same or flips into a valid strobogrammatic pair. For example, 101 appears identical when flipped, while 609 flips to become 609, and so on. The problem also specifies a few constraints to keep in mind. The value of n will always be between 1 and 14, and the output must list all strobogrammatic numbers in lexicographical order. Additionally, leading zeros are not allowed, except in the specific case where n equals 1 and the number itself is 0. There are a few additional considerations to handle edge cases. For odd values of n, the middle digit must be one of 0, 1, or 8, since these digits remain unchanged when rotated. For even values of n, every digit must form a valid strobogrammatic pair, such as 6 and 9 or 8 and 8. Another key requirement is that numbers with leading zeros, like 010 or 069, are not valid for n greater than 1. This ensures that all generated numbers conform to the problem's constraints while maintaining their strobogrammatic properties. To solve the problem of generating strobogrammatic numbers of a given length, we considered multiple approaches. The first approach is a brute force method. Here, the intuition is to generate all possible numbers of length n and then filter out the ones that are strobogrammatic. This involves checking each number by rotating it 180 degrees and comparing it with the original. The implementation uses a mapping of valid strobogrammatic pairs like 0 to 0, 1 to 1, 6 to 9, 8 to 8, and 9 to 6. However, the time complexity of this approach is 10 to the power of n asterisk n, as it generates all possible numbers and validates each one, making it computationally expensive for larger values of n. Additionally, it requires n space for temporary storage during validation. This inefficiency stems from the fact that it generates many invalid numbers, which we have to discard. The second approach, which is a recursive construction method, offers a more optimized solution. Instead of generating all numbers, we focus on directly building strobogrammatic numbers by placing valid digit pairs at symmetric positions. The idea is to use the valid strobogrammatic pairs and construct the number from the outermost digits inward. For odd-length numbers, the middle digit must be one of 0, 1, or 8. During each recursive step, a pair of valid digits is added to the front and back of the number, ensuring that only strobogrammatic numbers are constructed. This recursive construction approach is significantly more efficient, as the time complexity is reduced to 5n/2, where the 5 represents the limited number of valid digit pairs. This efficiency comes from the fact that we only explore valid combinations. The space complexity is n, which accounts for the recursion stack. The advantages of this method are clear: it avoids generating invalid numbers entirely, making it a focused and efficient solution. Another alternative we considered is an iterative approach, which is similar in intuition to the recursive method but uses a queue to construct the numbers iteratively. In this method, we start with either the middle digits if the length n is odd, or an empty string if n is even. We then iteratively append valid digit pairs to the front and back of the numbers in the queue until they reach the desired length. While the time and space complexities of the iterative method are comparable to the recursive approach, it tends to produce more verbose code, making it less elegant. Ultimately, we determined that the recursive construction method is the best choice for this problem. It is both intuitive and efficient, centering directly on valid strobogrammatic numbers without the overhead of filtering out invalid ones. Additionally, recursion provides a cleaner and more straightforward implementation compared to the iterative method. The key insight that makes the recursive approach so effective is that strobogrammatic numbers are defined by symmetry. This means we only need to place valid digit pairs at symmetric positions, reducing the problem to a manageable branching factor of 5 valid pairs. By constructing numbers recursively, we inherently avoid invalid cases, eliminating unnecessary computation. This efficiency stems from the limited number of valid digit pairs, which keeps the branching factor small regardless of the length n. However, as with any approach, there are trade-offs. Recursive methods rely on the call stack, which could theoretically lead to a stack overflow for very large values of n. That said, this is unlikely within reasonable constraints typically encountered in this problem. On the other hand, iterative methods are more memory safe, as they avoid recursion, but they require additional setup and result in more complex code. In conclusion, the recursive approach strikes the best balance for this problem. It is clear, efficient, and directly tailored to the constraints of constructing strobogrammatic numbers. This makes it the most suitable strategy for generating strobogrammatic numbers of any given length. To tackle the problem of generating all strobogrammatic numbers of a given length, we use a recursive approach. The first step is understanding strobogrammatic pairs. These are digit pairs that remain valid when viewed upside down. The valid pairs include 0 with 0, 1 with 1, 6 with 9, 8 with 8, and 9 with 6. These pairs are the building blocks of our solution. Using these pairs, we can recursively construct strobogrammatic numbers. The idea is to start with an empty string and expand it by adding valid pairs at both ends, ensuring the number remains strobogrammatic at every step. This recursive structure allows us to systematically generate all valid numbers of a given length. Now, let's focus on the base cases and the recursive expansion. For the base cases, if n is 0, we simply return an empty list since there are no strobogrammatic numbers of length 0. Similarly, if n is 1, the result is the single-digit strobogrammatic numbers, 0, 1, 8. For lengths greater than 1, we use recursion. We first generate strobogrammatic numbers of length n2, which are smaller subproblems. Then, we wrap these smaller numbers with valid pairs at both ends. For example, if the recursive call for n2 gives us 1, 8, wrapping with 6 and 9 produces numbers like 619, 916. However, we must ensure that numbers of length greater than 1 do not start with 0, as 069 would be invalid. Additionally, for odd-length numbers, the middle digit must be one of the single-digit strobogrammatic numbers, 0, 1, or 8. Analyzing the complexity, the time complexity grows exponentially with n because each recursive call generates multiple combinations. On the other hand, the space complexity is proportional to the recursion depth, which is O, n, and also depends on the space needed to store the results. Key insights for this problem include the divide and conquer technique, where we break the problem into smaller subproblems by focusing on numbers of length n2. This reduces the complexity compared to generating numbers from scratch. Symmetry is another important concept, as it allows us to leverage the mirrored nature of strobogrammatic numbers to avoid redundant computations. Finally, recursion itself simplifies the process, letting us focus on smaller subsets and iteratively combining results to form the complete solution. Edge cases require careful handling in this algorithm. Numbers of length greater than 1 must not have leading zeros, as this would result in invalid numbers. For odd-length numbers, the middle digit must be a valid single-digit strobogrammatic number, such as 0, 1, or 8. To implement this effectively, we use specific data structures. A list is used to store the results during recursion, allowing for efficient appending and retrieval of generated numbers. Additionally, a dictionary or a list of tuples is used to store the valid strobogrammatic pairs. This ensures that pairing and validation can be performed efficiently as numbers are constructed recursively. Let's walk through the algorithm with an example where n equals 3. The goal is to generate all strobogrammatic numbers of length 3. First, we make a recursive call to handle n2, which is 1. This generates the base cases 0, 1, 8. Next, we wrap each of these numbers with valid strobogrammatic pairs. For instance, wrapping 0 with pairs like 1 and 1 forms 101, while wrapping it with 8 produces 808. However, numbers like 000 are discarded because they start with 0. Similarly, wrapping 1 produces numbers like 111, 619, and 916, while wrapping 8 generates 888, 689, and 986. Finally, we combine all these results into the output: 101, 111, 818, 619, 916, 888, 689, 986. This systematic approach ensures that all strobogrammatic numbers of the desired length are generated efficiently. This implementation solves LeetCode problem 247, strobogrammatic number 2, which generates all strobogrammatic numbers of a given length n. The solution uses a recursive approach with helper functions. First, we define the pairs list containing valid strobogrammatic digit pairs 0, 0, 1, 1, 6, 9, 8, 8, and 9, 6. These pairs are crucial because they represent digits that remain valid when flipped and reversed. The build strobogrammatic function is a recursive helper that constructs strobogrammatic numbers. It takes current, representing the partially constructed number, and length, the target length of the number. If the length of current matches the desired length, the function joins the digits in current to form a complete number and appends it to the result list. Inside the recursion, the function iterates over each pair in pairs. For each pair, it ensures that leading zeros are avoided unless the number is 0. This is handled with a condition that skips pairs starting with 0 for the outermost recursion level, when len, current, equals 0, provided the length is greater than 1. The pair is then added to both ends of current, and the function recurses further. The recursion starts with an empty list and builds numbers layer by layer until the desired length is achieved. The result list accumulates all valid strobogrammatic numbers, which are returned at the end. This approach ensures correctness by systematically exploring all possible combinations of strobogrammatic digits while adhering to the constraints. It efficiently generates the results without unnecessary computations or invalid numbers. Here, we start the implementation by defining a method called findStrobogrammatic that takes an integer n as input, representing the desired length of strobogrammatic numbers. The first thing we do is define the valid pairs of strobogrammatic digits. These pairs include characters like 0 paired with 0, 1 paired with 1, and so on, ensuring that the digits look the same when rotated 180 degrees. Next, we initialize a result list to store the generated strobogrammatic numbers. To build these numbers, we use a helper method called buildStrobogrammatic. This method takes a character array current of size n, which will represent the current number being constructed. It also takes two indices, left and right, pointing to the positions in the array we are currently working on. Additionally, the method receives the pairs of strobogrammatic digits and the result list to store the completed numbers. The main idea here is to recursively construct the strobogrammatic numbers by placing valid digit pairs at the left and right positions of the number. Now, inside the buildStrobogrammatic method, we first handle the base case. If the left index exceeds the right index, it means the current number is fully constructed. At this point, we convert the character array into a string and add it to the result list. After handling the base case, we iterate over all valid strobogrammatic digit pairs. While doing this, we ensure the constraints of strobogrammatic numbers are met. For example, we skip pairs where the first digit is 0 if left is at the start of the number and the number length is greater than 1, as this would lead to invalid numbers with leading zeros. Similarly, if left equals right, the digit pair must be symmetric, such as 0, 1, or 8, because the middle digit in odd-length numbers must look the same when rotated. For valid pairs, we assign the digits to the left and right positions in the character array and then recursively call the method for the next positions, moving left one step inward and right one step outward. This process ensures that all possible strobogrammatic numbers of the given length are explored and added to the result list. To solve the problem of finding all strobogrammatic numbers of length 2, we start by understanding what makes a number strobogrammatic. These are numbers that look the same when rotated 180 degrees, such as 69 foot or 88. The valid digit pairs for this are 0 paired with 0, 1 with 1, 6 with 9, 8 with 8, and 9 with 6. Now, we initialize an empty list, current, to build our numbers, and set the target length n to 2. In the first recursive step, we loop through each pair. The pair 0 and 0 is skipped because leading zeros are not allowed. When we try 1 and 1, we add 1 to the beginning and end of current, forming 1, 1. Since the length of current now matches n, we add 11 to our result list and backtrack to explore other pairs. Similarly, for the pair 6 and 9, we form 6, 9, and since it satisfies the length requirement, we add 69 to the result before backtracking. This process continues for the other valid pairs, resulting in the numbers 88 foot and 96. At the end, our final output for n equals 2 is 11, 69, 88, 96. Now, for strobogrammatic numbers of length 3, we aim to build numbers like 609 or 818. The valid digit pairs remain the same as before. We start with an empty list, current, and set n to 3. In the first recursive step, we loop through each pair, again skipping 0 and 0 to avoid leading zeros. Trying the pair 1 and 1, we add 1 to the beginning and end of current, resulting in 1, 1. At this point, we need to add a middle digit, as the length of current is not yet 3. In the second recursive step, we insert valid middle digits like 0, forming 1, 0, 1. Since this matches the target length, we add 101 to the result and backtrack to explore other middle digits, such as 1 and 8, which yield 111 and 181. We repeat this process for other outer pairs like 6 and 9 or 8 and 8. For instance, using 6 and 9 with a middle digit of 0 gives 609, and using 8 and 8 with a middle digit of 1 gives 818. Eventually, we generate all valid strobogrammatic numbers of length 3, resulting in 101, 111, 181, 609, 619, 689, 808, 818, 888, 906, 916, 986. For strobogrammatic numbers of length 1, only single-digit numbers that appear the same when rotated 180 degrees are valid. These are simply 0, 1, and 8. We start with an empty list, current, and set n to 1. In the recursive step, we loop through each valid single-digit pair, directly adding 0, 1, and 8 to the result list, as no additional digits are required. The final output for n equals 1 is 0, 1, 8. A few key observations about the approach include the fact that the recursive depth corresponds to n/2 for even lengths and n/2 plus 1 for odd lengths. The use of backtracking ensures that all valid combinations are explored, while skipping the pair 0 and 0 at the outermost level avoids leading zeros, unless n is 1. This systematic method guarantees that we generate all possible strobogrammatic numbers for any given length. The time complexity of our solution is primarily determined by the recursive function, buildStrobogrammatic. This function generates all strobogrammatic numbers of length n by constructing the number pair by pair. The depth of the recursion is proportional to the number of digit pairs, which is ceil, n/2. This is because each recursive step appends one pair of digits symmetrically, and the process stops once half of the number is formed. At each level, we have 5 branching choices from the predefined strobogrammatic pairs, resulting in 5 ceil, n/2 total combinations. For numbers longer than one digit, we exclude pairs starting with 0 during the first recursive step to avoid leading zeros. However, this adjustment doesn't significantly alter the overall growth rate as n increases, so the branching factor remains effectively constant at 5. Now, let's consider the cost of constructing the strobogrammatic strings. For every valid number generated, we perform a join operation to create the final string representation. This join operation takes n time, and since there are 5 ceil, n/2 numbers generated, the total cost of string construction is n*5 ceil, n/2. Combining this with the cost of recursive generation, our overall time complexity becomes n*5 ceil, n/2. This means the time required grows exponentially with the size of n, though it is significantly optimized compared to brute force methods as we directly generate valid numbers rather than constructing and filtering out invalid ones. Next, let's explore the space complexity, which is influenced by both the recursion stack and the storage of results. The recursion stack depth is at most ceil, n/2, corresponding to the number of digit pairs added recursively. Since each recursive call uses O(1) additional space, the total stack space is proportional to O(n/2), which simplifies to O(n). On the other hand, the result list stores all valid strobogrammatic numbers. With 5 ceil n/2 numbers, each represented as a string of length n, the space required for result storage is O(n*5 ceil n/2). When we combine these two factors, the storage requirement dominates, giving us an overall space complexity of O(n*5 ceil n/2. To better understand the efficiency of this approach, let's compare it to a brute force method. A naive solution would generate all 10 n numbers of length n and then check each one to see if it is strobogrammatic. This involves a time complexity of O(10 to the power of n*n, as each number would take O(n) time to verify. The space complexity would also be O(10 to the power of n*n, for storing the valid numbers. In contrast, our optimized solution directly generates only the strobogrammatic numbers, reducing the total count to 5 ceil n/2. This makes the algorithm exponentially faster, with time and space complexities of O(n*5 ceil n/2. Moreover, the systematic generation ensures that best, average, and worst-case scenarios all share the same complexity, making the performance consistent across all inputs. Finally, let's solidify our understanding with a mathematical proof of the algorithm's big O complexities. The total number of recursive calls is 5 ceil n/2, as each level of recursion has 5 branches and the maximum depth is ceil n/2. For each generated number, the string construction step adds an O(n) cost. Multiplying these two factors gives us a total time complexity of O(n*5 ceil n/2. On the space side, the result storage dominates, requiring O(n*5 ceil n/2 space for all generated strings. This efficiency stems from leveraging symmetry and directly generating valid strobogrammatic numbers, avoiding the exhaustive search space of brute force methods. As a result, the algorithm achieves a significant improvement in both time and space efficiency. When working on this problem, there are some common mistakes that can trip us up. First, it's crucial to handle edge cases properly. For instance, when n equals 0, the result should be an empty list, and when n equals 1, single-digit strobogrammatic numbers like 0, 1, and 8 are valid. Overlooking these can lead to incorrect outputs. Next, be careful not to include invalid numbers. For example, while 69 or 96 are valid strobogrammatic pairs, a single 6 or 9 is not, especially for odd-length numbers. Another common pitfall is allowing leading zeros in multi-digit numbers. Numbers such as 069 are invalid because they start with a 0, which is only acceptable when the number itself is 0. Base cases in recursion also need to be handled carefully. For instance, if we don't return the correct middle values like 0, 1, 8 for odd-length numbers, the recursion will fail for larger inputs. Lastly, inefficient string concatenation can slow things down significantly. Instead of concatenating strings repeatedly in a loop, use a list to collect results and join them later for better performance. To succeed in interviews with this problem, focus on mastering the core pattern of strobogrammatic numbers, which relies on symmetric pairs like 0 to 0, 1 to 1, 6 to 9, 9 to 6, and 8 to 8. Understanding and applying this pairing logic is key to building efficient solutions. When it comes to approach, recursive methods, which are top-down, can feel intuitive but might run into memory limitations for larger inputs. Iterative or bottom-up approaches avoid this issue and are preferred when constraints are tight. Optimization is another area to consider. Techniques like memoization or iterative strategies can help eliminate redundant computations, especially in cases with overlapping subproblems. During interviews, always clarify constraints up front. For example, ask if leading zeros are allowed or if there are specific edge cases to address. This not only demonstrates thoroughness but also ensures your solution aligns with the problem requirements. Finally, it's worth noting some related problems, such as LeetCode number 246, which checks if a number is strobogrammatic, or number 248, which counts strobogrammatic numbers in a range. These can provide additional practice and insights into symmetry-related concepts. One common approach to solving this problem is by using recursion. Here, we build from the middle of the number outward, adding valid strobogrammatic pairs at each step. For example, the base case for odd-length numbers would include the single digits 0, 1, and 8, while the base case for even lengths would start with an empty string. From there, we recursively generate smaller strobogrammatic numbers and expand them by adding pairs like 0 to 0, 1 to 1, 6 to 9, 9 to 6, and 8 to 8 at both ends. A key detail is to avoid adding 0 at the beginning of numbers unless the number itself is 0. While this approach is straightforward and relatively easy to implement, it can become memory-intensive due to the depth of recursion, especially for larger values of n. To address this, we can consider iterative alternatives, which we'll discuss shortly. Another viable method is the iterative approach. Here, we start with the base cases, such as 0, 1, 8, for n equals 1, and iteratively add strobogrammatic pairs to build longer numbers. This avoids the recursion depth issues seen in the recursive method, making it more memory efficient. However, implementing it can feel less intuitive since it requires careful bookkeeping of intermediate results. Another technique, though less practical, is brute force with filtering. This involves generating all possible numbers of length n and filtering out those that aren't strobogrammatic. While this approach is simple conceptually, it's highly inefficient for larger n because the number of candidate numbers grows exponentially. As a result, it's generally not recommended unless n is very small or time complexity isn't a concern. Great job! Today we tackled strobogrammatic number 2 using a recursive approach. We discussed the symmetry of strobogrammatic numbers, explored the algorithm's efficiency, and highlighted key takeaways. Thanks for watching. Feel free to like, share, and subscribe for more problem-solving sessions. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!